Welcome to this video on Advanced Enterprise Network Architecture and Security. This video I'm going to be detailing the Active Directory logic and global forest topologies, as well as identity security and policy overrides, and finishing off with advanced disaster recovery and directory repair. This video is best for IT security practitioners or people looking to excel in exams covering enterprise network security. I'll also be doing live demos in an Azure virtual machine as well to ensure that the theory concepts make the most sense in a practical way. First thing I want to be talking about is visualizing truss, trees, and forests. So the first thing that we have is the domain, which is the workspace. The foundational administrative boundary, it contains the actual objects you interact with daily, like users, groups, computers, and printers. How it works, all objects within the domain share a common database, security policies, and an authentication boundary. If you change a password in a domain, that change replicates to all domain controllers within that specific domain. It uses a standard domain name systems, so DNS structure, for example, headquarters.com. So we have trees, which is the family line, a collection of one or more domains grouped together in a hierarchical namespace. How it works, when you add a child domain to a parent domain that became part of the same tree, domains in a tree automatically form two-way transitive truss, meaning users in the parent domain can access resources in the child domain if granted permission, and vice versa. They must share a DNS namespace. For example, the parent company.com, the child would be uscompany.com, and the grandparent could be dev.us.company.com. We then have forest, which is the entire ecosystem. This is the highest organizational container in Active Directory. It is a collection of one or more independent trees that share a common global catalog, directory schema, and network configurations. I'll explain that in a second. But how it works is that the trees inside a forest do not need to share a continuous naming structure. However, because they are in the same forest, they trust each other automatically via transitive truss. The forest creates the ultimate security boundary for your organization. The name, so a forest takes the name of the very first domain created in it, the root domain. For example, a single forest could contain two entirely different business entities. So tree 1 could be company.com and its children, and tree 2 could be acquiredbrand.org and its children. This image sort of explains what I just talked about. So we have the domain, we have the users, computers, the tree is connected domains, and then the forest is multiple trees, collection of trees. So directory schema. This is the master blueprint or rulebook for the entire forest. What it does is it defines every type of object that can exist, users, computers, and the attributes associated with them. Phone number, email address, employee ID. Key point is that there is only one schema per forest. If you modify it, like adding a custom attribute for a new software integration, that change applies to every single domain in the entire forest. Global catalog, the forest-wide searchable index. What it does is instead of forcing a search to crawl through every individual domain controller across the globe, the GC holds a partial read-only copy of every object in the forest. It keeps only the most commonly searched attributes like first name, last name, and email, etc. Key points is it allows the user in the US domain to instantly find the email address of a colleague in the European domain without a slow, complex cross-domain query. Network configuration. The configuration partition is the operational map of the physical network layout. What it does, it stores the replication topology, physical Active Directory sites, which map to the IP subnets, and transport protocols. It tells Active Directory exactly how and when to replicate data between domain controllers. For example, domain controller A and B are in the same building over high-speed LAN, so replicate instantly. Domain controller C is across an expensive Wireless area network links only replicate once an hour. So as you can see in this diagram, we have 3 trees and we'd have 6 domains. 2, 3, 4, 5, 6, all within the global company forest. So in this demo, we are expanding our enterprise infrastructure by deploying a multi-domain Active Directory forest across different subnets. Our core environment is already anchored by swin22dc1, which serves as our forest root domain under corp.local. The first thing I did was demote the Active Directories in order to remove the old infrastructure and set up a new forest, which you will see as the demo progresses. Just a note on the IP addresses. What we're doing now is we're just making sure that all the IP addresses are within the correct sort of ranges and making sure that the preferred DNSs always point to the forest root, which is DC1. You'll be able to notice that SVR1 is a child domain based on its IP address, whereas SVR2 is a tree domain because it's in a completely different domain. I just wanted to point that out and just making sure that connectivity works between the 3 different domains. Next up, we are looking at swin22 SVR2. For this server, we chose to add a completely new domain to an existing forest, creating a new tree domain named brand-b.com. Because this operation requires administrative authority over the entire infrastructure, we supplied the forest root credentials using corp.local/administrator. Once the configuration wizard passed its prerequisite checks, the server went through its promotion phase and rebooted as a brand new tree root. Next, we shifted our focus to swin22 svr1 to build a child domain. In the deployment wizard, we selected child domain and specified corp.local as our parent. After changing our credentials to target the forest root administrator, we kicked off the installation. With both promotions complete, we logged back into swin22dc1 to verify our architecture using Active Directory domains and trusts. As you can see on screen, uk.corp.local is perfectly nested under our root, and brand-b.com sits alongside it as a peer tree domain. To wrap things up, we successfully tested cross-domain authentication by logging into our child domain using the forest root administrator account. Our multi-domain structure is officially verified, stable, and ready for the next phase, deploying our read-only domain controller on server 3. Now we're going to move on to FSMO roles, domain versus forest uniqueness. So in Active Directory, flexible single master operation FSMO roles exist because certain tasks are too critical or sensitive to handle multi-master replication conflicts rather. If two domain controllers, DCs, tried to make these changes simultaneously, it would break the directory. To prevent this, specific DCs are assigned as the sole authority for these tasks. Here is why some roles must be unique to the entire forest, while others only need to be unique within a local domain. So the forest-wide roles, one per forest, is the schema master, prevents database corruption by ensuring only one DC modifies the global object blueprint. Domain name master prevents network routing conflict by ensuring domain names aren't duplicated when added or removed. We also have domain wide roles, one per domain. The RID master prevents security conflict by handing out unique ID blocks to local DCs for creating users and computers. PDC emulator prevents login frustration by instantly syncing password changes, tracking authentication failures, and managing network time. We also have infrastructure master. So this prevents broken references by updating local groups when members from other domains are changed or deleted. Now here are two concrete scenarios where letting any domain controller handle the task multi-master causes immediate breakdown, showing why giving a specific DC sole authority is required. So for the first example with the forest-wide scenario, we have the clashing software upgrades. The setup. A global enterprise operates at a single Active Directory forest. DC London handles the European offices. DC Tokyo handles the Asian offices. Both are allowed to modify the forest-wide database blueprint, the schema, under a multi-master rule. The conflict. At the same time, the two IT teams deploy different corporate software suites that require modifying the schema to create a custom user field called corporate ID. In London, the HR software installer contacts DC London and creates corporate ID as an integer, numbers only like 1, 2, 3, 4, 5. In Tokyo, the logistics software installer contacts DC Tokyo and creates corporate ID as a string text like EMP 1, 2, 3, 4, 5. Because it is multi-master, both DCs accept their local updates successfully. What happens is that overnight the two DCs attempt to replicate their database changes to each other. When the replication engine tries to merge them, it hits a fatal paradox. The data structure rule dictates that a single attribute cannot be both a number and a text. Replication locks up entirely between Europe and Asia. The directory database enters a corrupted state, and future network schema updates are blocked globally until engineers manually reconstruct the database. The fix is a forest sole authority. So by giving one single DC the role of schema master, this disaster is impossible. The Tokyo installer would contact the schema master, lock the attribute name, and when the London installer tried to create it a second later, the schema master would reject it with an attribute already exists error. Local domain scenario. The security ID car crash. The setup. A university has a single domain, campus.local, with thousands of students registering for classes on orientation day. DC North handles registrations at the North Campus. DC South handles registrations at the South Campus. Both are allowed to independently generate security identifiers under a multi-master rule. Conflict. Every user account needs a globally unique SID to access files. This SID is made of a domain ID plus a unique trailing number called a relative ID. At North Campus, a student named Alice registers. DC North generates an account for her and assigns her the next available number in its head, RID 5001. At South Campus, at the exact same second, a student named Bob registers. Because DC South hasn't yet synced with North yet, it checks its own count and assigns Bob the exact same number. The disaster is that Alice and Bob have the exact same security ID. The next day, Alice logs into a lab computer and submits her private medical accommodation forms to a secured network folder. Because Bob shares the exact same SID, the file server sees Bob and Alice as the exact same person. Bob logs in, opens the folder, and accidentally granted full access to Alice's private documents, creating a massive data breach. The fix. By giving one single DC the role of RID master, DCs are no longer allowed to invent RID numbers on the fly. Instead, DC North and DC South must request a pool of numbers. For example, North gets 5,000 to 5,500, South gets 5,501 to 6,000. From the master ahead of time, Alice gets 5,001, Bob gets 5,501, and the identities never cross. We opened an administrative PowerShell prompt on our root DC to audit our flexible single master operation or FSMO roles by running the command netdom query FSMO, we can see exactly where the core logic of our forest lives. As the output on screen shows, all 5 roles, the forest-wide schema and domain naming masters alongside the domain-wide PDC, RID, and infrastructure masters safely reside on swin22dc1.corp.local. This is exactly what we expected to see in a freshly deployed forest. Our infrastructure is completely verified, healthy, and ready for our upcoming read-only domain controller deployment. We're now going to look at identity security and policy overrides. First thing that we're going to look at is fine-grained password policies, precedents. So the core problem is that one policy fits all. Historically, Active Directory password rules were tied directly to the default domain policy. This meant an organization was stuck with a single set of rules for the entire domain. If administrators needed ultra-secure 16-character passwords, every regular user and service account was forced to use 16-character passwords too. So the solution is password setting objects, PSOs, with fine-grained password policies breaks this restriction by using PSOs. Instead of applying rules to the whole domain, you create separate policy objects inside the AD system container and link them directly to specific users or global security groups. It allows you to easily isolate risk. So general staff, for example, might only need a standard 8-character policy, but admins might need a strict 16-character policy, and service accounts might need a non-expiring policy. The rules of precedence. If a user is targeted by multiple conflicting PSOs, Active Directory decides the winner using 2 strict rules. So lower integer wins. PSOs use a precedence number. A lower integer value means higher priority. And the second rule is that direct link trumps group link. If a PSO is attached directly to a user account, it automatically wins over any PSO attached to the security groups, regardless of what the precedence integer is. Here's a real-world scenario demonstrating how Active Directory resolves conflicting password policies using these exact rules. So the setup is a corporate IT environment. Imagine an enterprise domain with 3 separate password setting objects configured in the Active Directory Administrative Center. Policy A, linked to all employee groups. Rules is that it's 8-character minimum, expires every 90 days, precedence number 50. Policy B is linked to domain admins group. Rules 16-character minimum, expires every 30 days, high complexity, precedence number 10. Policy C linked directly to a single user account. 20-character minimum, expires every 15 days, ultra secure, precedence number 100. So the scenario 1 is group versus group, lower integer wins. Dave is a senior network administrator. Because of his job roles, he belongs to both the all employees group and the domain admins group. Conflict: the Active Directory sees that Dave is being targeted by two different group policies, policy A, precedence 50, and policy B, precedence 10. The winner is policy B, domain admins, because Active Directory compares the precedence integers. This is 10 compared to 50. Policy B has a higher priority. Therefore, Dave is forced to use a stricter 16-character password. Scenario 2, direct link versus group link. Direct link trumps all. The company hires an external cybersecurity auditor named Sarah for a 2-week project. To give her maximum access, they place her account into the domain admins group, triggering policy B. However, due to the strict compliance requirements, the Chief Information Security Officer, CISO, explicitly assigns policy C directly to Sarah's individual user account. The conflict: Active Directory looks at Sarah's account and sees two competing forces. She inherits policy B, precedence 10, from her group. She has policy C, precedence 10, attached directly to her user object. The winner is policy C, because even though policy C has a much higher precedence number, 100 versus 10, the direct link rule completely bypasses the integer check. The policy is explicitly pinned to a specific user object. It overrides any and all group level inheritance. Sarah must use an ultra secure 20-character password. We are setting up fine-grained password policies, or FGPP, to apply customized password restrictions to specific high-security groups. We begin by opening the Active Directory Administrator Center, navigating to the System container, and opening the Password Settings container. By creating a new Password Settings Object, or PSO, we are presented with a variety of security controls. The most critical field to note here is precedence. Active Directory uses this integer value to resolve policy conflicts. If a user is subjected to multiple PSOs through different group memberships, the policy with the lowest precedence number wins. By setting this to an integer like 10, we ensure it overrides the weaker default domain policy for our targeted users. Moving on to group policy loopback processing modes. The core problem is user versus location. Normally, group policy objects, GPOs, are split into two halves. Computer configuration applies to the machine, no matter who logs in, and user configuration applies to the user, no matter what machine they sit at. By default, if a CEO logs into a public terminal, like a warehouse, kiosk, a training room PC, or a conference room laptop, their corporate user GPOs follow them. This means that personal wallpaper, unrestricted internet access, and map network drives suddenly appear on a wide, open, publicly facing machine. This is a massive security risk and can disrupt the functionality of a dedicated terminal. Solution: loopback processing flips this behavior on its head. It tells Active Directory when someone logs into this specific computer, prioritize the computer's physical location over the user's corporate identity. It allows administrators to force strict environment lockouts based entirely on where the login is happening rather than who is logging in. The two modes. How the override happens. When you enable loopback processing on a computer GPO, you must choose between two modes to handle the conflict. Merge mode, the collaborated append. In merge mode, the Active Directory tries to give the user the best of both worlds, but the computer gets the final say. The process: the system gathers the user's normal user GPOs first, then it looks at the computer's organizational unit and grabs the user configuration settings tied to that computer. It appends, merges them to the user's session. Conflict resolution. If there is a direct contradiction, e.g. the user GPO says allow control panel, but the computer GPO says block control panel, the computer linked GPO wins. Replace mode, an absolute lockdown. In replace mode, Active Directory completely ignores the user's corporate identity. The process is that the system completely throws away the user's standard list of user GPOs. It acts as if they don't exist. Instead, it only looks at the OU where the computer object resides and applies the user configuration settings linked to that computer container. The result is the user gets a completely clean, standardized lockdown environment tailored precisely for that machine. For example, a kiosk desktop with a single browser icon, no start menu, and no access to local drives, regardless of whether they are temporarily guest or the domain administrator. For example, imagine a training room PC configured with loopback processing. Under merge mode, an instructor logs in and gets their personal department network drives mapped from their user GPO, but the computer policy forces the screen to lock after 5 minutes of inactivity and disables the USB ports. Under replace mode, the same instructor logs in and gets none of their personal drives or desktop shortcuts. They see the exact same generic lockdown student desktop environment that a guest student would see. We move on into managing unique user environments using group policy loopback processing. In standard operations, user configuration settings follow the user account across the network. But for specialized environments like computer labs, kiosks, or terminal servers, we want the physical computer's location to override who's logging in. To demonstrate this, we created a new loopback policy inside Group Policy Management and edited the GPO, drilled down under Computer Configuration, Administrative Templates, System, and Group Policy. We located and enabled the loopback processing mode setting. Under the option drop-down, we can select between merge and replace modes. Selecting replace tells the operating system to completely drop the user's normal personal environment settings and strictly enforce the explicit lockdown policies tied to this computer's specific organizational unit. Final thing that I want to touch on is advanced disaster recovery and directory repair, authoritative versus non-authoritative AD restore. The core metric, update sequence numbers, USNs. Active Directory doesn't track changes using clocks, which can drift. It uses an internal counter called a USN. Every time an object is changed or deleted, the local DC bumps its USN up by 1. DCs sync by asking partners for any changes with a USN higher than the one last received. Non-authoritative restore, catch me up. What it does, restores a broken DC back to health using an old backup. The process is that the DC boots up with old data and low USNs, then contacts healthy network partners, realizes this database is outdated, and lets standard inbound replication overwrite its old files to catch it up to the present day. It's best for recovering from a physical server crash or hardware failure. Authoritative restore, I'm the boss. What it does is it recovers an object like a user or an entire organizational unit that was accidentally deleted by an admin. The process is first to isolate and restore, disconnect the DC from the network, boot it into a DSRM, and restore the database from a backup. The deleted object is now temporarily back on this single machine. Launch ntdsutil, open the command line and run this ntdsutil to target the exact distinguished name DN of the deleted object. Example, OU is equal to accounting, DC is company, DC local. The USN bump, run the authoritative restore command, ntdsutil artificially inflates the object's USN by a massive buffer, typically 100,000 per day since the backup. Reconnect and overwrite. Reconnect the DC to the network. When it syncs, its massive USN forces all other DCs to accept the restored object as the absolute newest truth, instantly undeleting it across the entire forest. So the result is when the DC reconnects to the network, its massive USN forces all other DCs to accept the restored object as newer update, effectively undeleting it across the entire forest, which we just covered. It's best for recovering from accidental administrative deletion. For our final demo lab, we booted swin22dc1 into DSRM and opened up ntdsutil to look at the metadata cleanup utility. But when we typed connect to server swin22dc1, we immediately hit this error. There are no more endpoints available from the endpoint mapper. This happened because we are in directory service repair mode. In this mode, the local Active Directory service on this machine is completely turned off. Because it's offline, ntdsutil has no active database endpoint to talk to on this server. If we want to successfully run this command, we either have to point it to a different domain controller that is currently online, or boot this server back into normal mode first. Obviously, this is only done if a fail happens. Obviously, the servers are up and running now, hence we don't need to do this in my specific scenario. Thank you very much for watching this video on advanced enterprise network architecture and security. If you want me to go deep dive, there's a couple more topics that we can touch on, but if you leave a comment, I can make another video on that in the future. Thank you very much.